Today I will talk about quasi-local mass and the geometry of scalar curvature. Actually, this talk is based on some joint work with my students and a postdoctor. Okay, let's get started from some well-known facts about scalar curvature. By definition, scalar curvature is a trace of Ricci tensor, which is a symmetric two tensor on a Riemannian manifold. And a nice way to understand this scalar curvature is to look at the volume of the small geodesic ball, which is denoted by BRP. And here is the formula. Now, capital RP is scalar curvature of the at P. So by this formula, we see that for any fixed small geodesic ball, the largest scalar curvature is, the smaller the volume of B's. In the 60th of last centuries, French mathematician Riemannian found that there are some differential manifolds that admits no positive scalar curvature matrix. Since then, the problem to ask under what kind of condition so that a differential manifold could admit or cannot admit a positive scalar curvature matrix to be one of central problems in Riemannian geometrics. To me, it's interesting to see that a scalar curvature sometimes can be explained as a energy density in general relativity. Here, GR refers to general relativity. So, because of this, the geometrical scalar curvature problems usually have deep relations with energy problem in general relativities. Now, this is some well-known facts. Today, I'll talk about Chromophilian problem. This problem was proposed by Professor Gromov about 4 years ago. Now, here are the formulations. Let this triples be a Bodic date which consists of Riemannian manifold sigma gamma. And H is a smooth function defined on sigma, which will serve to be a mean curvature later. Now, the problem is to find a condition. Under that condition, this triple would or wouldn't admit a fill-in by a Riemannian manifold, which is denoted by omega g, so that H, this function, is a mean curvature of the boundary in omega n. Here, mean curvature always with respect to out-volume normal vectors. And the third condition is, as a second condition is gamma is induced metric of G. And the third one is that scalar curvature has a given lower bounded. Here, sigma is given lower bounded. 1 year later, Professor Gromov raised for a more specific problem. That is, let X be a compact Riemannian manifold with given lower bounded, and then he conjectures that the total mean curvature has a uniform upper bound. That upper bound depends only on boundary, y and gamma, and y and lambda, and sigma. Here, sigma is the given lower bounded of the scalar curvatures. Now, in those two problems, ambient manifold can be given a priori. Even in this simple case, the problem is also interesting. Now here, I would like to give a remark. As we know that scalar curvature involve a second derivative of Riemannian metric G, while mean curvature are only first derivative of metric G, and which served as kind of boundary condition. Okay. Now, we will see.
Excuse me.
Yeah.
Perhaps we can pause a tiny bit. We'll just pause on the conjecture for a little bit. I don't actually see Misha among the participants. Misha Gromov. I don't know if he got disconnected, so maybe we just wait a tiny bit.
I see him.
You see him now?
Yep.
Okay, great. Thank you. Okay, sorry, you may continue.
No, I'm here, yeah.
Yeah, okay, great.
And show my existence, yeah.
Thank you. You've proven your existence.
Okay, may I go on? Yeah.
Yeah, sorry, I'm so sorry.
Okay, it's okay. Now, we will see later that those two problems has relation with quasi-local mass. So let me give a very brief description of what is quasi-local mass. Roughly speaking, quasi-local mass is a geometric quantity of two-dimensional surface sigma, and it measures how much energy or how much mass contained in domain enclosed by this sigma. And the quasi-local mass usually depends on geometry of sigma, like mean curvature, area, etc. Now, let me show you examples. The first example is so-called Brown-York mass, which was introduced by two physicists named Brown-York, I think about 30 years ago. Let omega G be a compact Riemannian manifold with convex boundary. That is, the Gaussian curvature of the boundary is positive. And then by the classical result due to Professor Nierenberg, we know that the boundary can be isometric embedding into Euclidean space. And the embedding image is still denoted by sigma. And we also have mean curvature of the embedded image, which is denoted by H0. And then Brown-York mass is simply defined by the integral of difference of two mean curvatures. And as we know that such kind of isometric embedding is unique up to a rigid motion in Euclidean space. So the H0 is completely determined by induced metric of sigma. And then by this formula, we see that the larger the mean curvature H, and the smaller this Brown-York mass will be. Okay. So roughly speaking, Brown-York mass measures the difference between the compact Riemannian manifold omega G with non-negative scalar curvature metric. Here, NSC refers non-negative scalar curvature metric, and with convex domain in R3. Wang, St. Yao, and Marisa Liu has a serious generalization of Brown-York mass in, I think, in those 20 years, during these 2 decades. But I will not go into detail here. And our second example is so-called Hawking mass. So now let this be a compact Riemannian manifold. This time, the boundary may not necessarily convex. And we defined Hawking mass by this formula. Here, this is square root of area of the boundary. And this is the Wormhole functionals. And by this formula, we also see that the largest mean curvature H is, and the smaller the Hawking mass will be. It is not so difficult to show that for all compact surface in Euclidean space, and the Hawking mass is non-positive. And it equal to 0 if and only if sigma is a round sphere. So we can say that Hawking mass measures the difference between omega G with a round ball in Euclidean space. Okay, this is 2 examples. Now, here is a summary for quasi-local mass. First, it is a geometric quantity of the boundary of the domain. The second one is quite interesting to me, at least. According to some physical law, it should be non-negative, where the scalar curvature is non-negative. And the third one is that the large the mean curvature is, the smaller the quasi-local mass will be. So with those facts in mind, intuitively, the answer to Professor Gromov's conjecture should be affirmative. That is, it may have a uniform upper bounds for the total mean curvature among of the given boundary among all non-negative scalar curvature field in. Okay. Okay. It seems to me that it's the following problem, which you call the embarrassing question by Professor Gromov, is a very natural one, and we have to solve it before we go any further in the investigation of the field-in problem. Now, so here's the problem. Let X be any compact manifold, and Y be its boundary. Given any Riemannian metric gamma on Y, the problem is to ask if we can extend gamma to a Riemannian metric G, which is defined on the interior part of X, so that the scalar curvature is positive. Okay. There is a relating problem, which was early result proved by Professor Gromov. That is, for any complex manifold with non-empty boundaries, there we can always find a metric, it has a positive sectional curvature, but it has no requirements of the induced metric of the boundary these times. Okay. Now, in last years, my students Wang and my postdoctor G.D.Wei proved that we do have such extensions. Now, more precisely, that let X be any compact manifold, Y be its boundary, and given a Riemannian metric, any Riemannian metric on the boundary Y, we can always extend gamma to a Riemannian metric which is defined on interior of X, so that the scalar curvature is positive. And Professor Gromov also raised some further problems on the extension of positive scalar curvatures in his 4 lecture notes. Now, here's one of them. So that is, let X be a compact manifold, and he asks that does X admit a Riemannian metric G so that the scalar curvature has given positive lower boundary, which is denoted by sigma plus. And meanwhile, the mean curvature of the boundary has a given such a low bounded m minus, or m minus should be negative. And it is also even unclear for a specific manifold like n-dimensional torus dilated ball, or a manifold, an underlying differential manifold is homomorphic to a compact hyperbolic manifold with totally geodesic boundaries. Now, let me give you a remark. So that is, if we pick up this specific manifold, that n-dimensional torus dilated ball D, then there's no positive scalar curvature metric on it, so that the mean curvature of the boundary is non-negative. Here, mean curvature is always with respect to outward uninormal vectors. Suppose this is not true. That is, we can find a Riemannian metric that it is positive, scalar curvature interior part is positive, and the mean curvature is non-negative. Then we can double it and get a manifold like this. And because the mean curvature at this boundary, at the two sides of the boundary is non-negative, and we can smoothify and get a smooth metric on the resulting manifold with positive scalar curvature everywhere. And this is a contradiction to Shen-Yao's result, because its topology is Tn connected with Tn. At least for m less than 7, there's no positive scalar curvature metric on such a manifold. Okay. Now, there is a nice application of our extension theorem which is due to Peng-Zhi-Miao. Now here is his theorems. Let sigma be boundary of some compact n-dimensional manifold, which is denoted by omega n, and given any Riemannian metric gamma of the boundary, then we can find a constant which is denoted by h naught, and h naught depends only on sigma and gamma. And if the mean curvature is at least bigger or equal than h naught pointwisely, then there do not exist a non-negative scalar curvature fill-in of these triples. This is give an answer on Professor Gromov's questions, which I mentioned before. Okay. Now, the following picture illustrates the main idea of the P.Liu.
But constant is positive.
Sorry?
Constant is positive.
Yeah. I will show you how to define this H naught later.
Yeah.
Okay. Now, this picture illustrates the P.Liu, a main idea of the P.Liu on Peng-Zhi-Miao's result. Let omega naught be any fixed manifold whose boundary is sigma. And then we do connected sum with an n-dimensional torus. And the resulting manifold is still denoted by omega naught. And now let gamma be the Riemannian metric defined on sigma. Then by our extensions theorems, such a gamma can be extended to a Riemannian metric in the interior part omega naught, which denoted by G tilde, so that the scalar curvature of G tilde is positive. Okay, and then we have mean curvature, which is denoted by H1, and we define H naught in like this. So it is always positive. Then we claim that any triples sigma gamma H admits no non-negative scalar curvature metric fill in if H is at least H naught, pointwise this. Suppose this is not true, then we can find a fill in omega n G so that its boundary date is this ones. And then we can glue in this thing and that thing together along the boundaries. And we know that the mean curvature at two sides satisfies this. And then we can smoothify and get a new smooth metric with positive scalar curvature everywhere. While this the resulting manifold, so topology of resulting manifold is like Mn connection with Tn, and this admits no positive scalar curvature metric. So this is the idea of the proofs. Yeah. Any questions? Okay, if there are no questions, I will go on. Now, to investigate the fill-in problems, we need the following notations. The first one is that let sigma be any Riemannian manifold. We defined quantity lambda plus be the supremum total mean curvature among all the non-negative scalar curvature fill-in of these triples. And we requires that we assume that the mean curvature at the boundary is positive, so we denote lambda plus. And we can also define a similar quantity like this. Now, in these definitions, there's no assume no requirement of positivity or mean curvature. And actually, for n equal to 3, this quantity was introduced by Mantelidis, P.Liu 5 years ago. They use this to study general Brown-York mass. Of course, it is easy to generalize these quantities by this. Now, in this in definition of this, we assume scalar curvature has such a lower bounded. Here, kappa may equal to 1, or may equal to 0, or may minus 1. If equal to 0, then this one equal to that one. This quantity is equal to that quantity. So this is a simple generalization of this. Now, with those notations, we can reformulate Professor Gromov's conjecture in the following way. That is, lambda kappa of a given Riemannian manifold is always bounded by such a constant C, which depends only on sigma gamma kappa. And by the definition, we have that lambda plus kappa of the Riemannian manifold cannot be bigger than lambda kappa. To my knowledge, there's very few results on this. We only have some result on lambda kappa, upper bound or lambda plus kappa on this. Now, let me show you some of them. The first result, I think, is by the positivity of Brown-York mass. Actually, it is easy to see that positivity of Brown-York mass, when n equal to 3, that the surface case, the positivity of Brown-York mass is a necessary condition for these triples have non-negative scalar curvature fill in, but it is far from sufficient. And Geometrically, P.Liu, Langfei 10, Mantelidis have a serious interesting work in the low dimensional case, n equal to 3 case. So how about the high dimensional case? We do have such a result. Okay. Let this denoted by a CK smooth partial scalar curvature of on the unit sphere, and so the standard sphere unit metric lambda, this one is in this set, and let gamma be any metric in this set, and we assume there is a smooth path in this set, so a joint gamma and unit sphere metric, which is called the isotopic to standard sphere metric. Under such a condition, we can show that we can say is a constant depends only on H naught, depends only on gamma, so that the lambda plus of this Riemannian manifold cannot be bigger than H naught. And this is a joint work with Wang, G.D.Wei and J.Chen about I think it's 2 years or 3 years ago. Now here's a remark. According to a result due to Fernando Marcos, if n equal to 3, for any positive scalar curvature metric on the S3 is isotopic to a unit sphere metric. So this condition is automatically true if n equal to 3. Okay, this is the result for high dimensional case.
So remind me just again this lambda plus, I've forgotten. Plus means you allow not positive, or do you or insist positivity of the mean curvature? I forgot.
Yes,
the definition was too fast. Lambda plus.
Yeah, for lambda plus we need the positivity of mean curvature.
Positive mean curvature.
Yeah.
Okay.
Mm-hmm. Yeah. Any questions? Because I use the argument of quasi-spherical metric here, so we needed to assume positivity of mean curvature at the initial date. Okay.
Okay.
Now the next question is we want to study the explicit value of this quantity. What's the explicit value of this, and what is the explicit value of this total mean curvature? So, now let me show you very simple examples. So let's pick up its standard unit sphere and let H be positive. So this is a bionic date. And now we have several two results. First, the result due to Pengzi Miao. He was able to show that such kind of minimal mean curvature cannot be bigger than 2. And the equality holds if and only if the field in omega g is unit Bohr. And the second one is due to Ken and I, that we can show that in this case, the total mean curvature cannot be bigger than 8 pi. And the equality holds if and only if omega g is unit Bohr. In both results, positive mass played important crucial roles. So we can say that those two problems have deep relation with positive mass theorems. Actually, we have a high dimensional generalization of this. Now, here's a precise statement, which is a joint work with Wang and G.D.Wei. We can show that the lambda plus of standard sphere equal to this one. This is volume on standard sphere if and only if the positive mass theorem is true on asymptotic flat manifold, on any asymptotic flat manifold. This is the first result. The second result is that
what is the problem? What meaning this if? When
if and only if. That means if this is true, that means positive mass for any asymptotic flat manifold is true.
No, and, I think positive mass is true at least for all spin manifolds. It's proven. So what is the issue of not being true? I'm somewhat confused.
No, for any, not only spin manifold, for any.
So this is the point, not necessarily spin, yeah.
Yeah, not necessarily spin. Yeah.
So you don't accept. So you don't accept this Schoen-Yau techniques, because if you accept Schoen-Yau and apply this trick by Lockham, I forgot how it's called. You can prove this positive mass conjecture, reduce to almost flat case, and then reduce to the case of somebody connected some with the torus.
But I mean, if this equality is true, then positive mass is true.
No, but another way around. Yeah. Because you do know, if you accept Schoen-Yau paper of singularities, the connected sum of manifold with the torus has no positive curvature metric. Now, if you have any positive mass for general manifold, it reduces to the case when manifold asymptotically Euclidean, not just flat Euclidean. And if it is asymptotically Euclidean, then you can make the torus out of it by periodically repeating it, and then you reduce to Schoen-Yau. And that is always true.
Excuse me, updates ready to install.
Oh, I apologize for this computer. So I don't understand. If you don't accept Shun-Yao, of course, and think it's not, the proof is not published or whatever, then of course it's conditional. But if you accept their paper, then it follows from their paper.
I will show you the proof later. Okay. I will prove these theorems later.
So I think, if I might speak, I think he's saying, let's just not know if Shane Yao is correct or not. Then we have this if and only if statement. So the minute everybody believes Shane Yao's proof, then this will be true too.
Right. If you believe Shun Yao, then you remove if. But before that, you mention Shun Yao for all dimensions. Because this is what I'm surprised. And you refer to their paper of 2018, and you refer to their paper. So you accept it. So I didn't ask you. Well, I believe you checked their proof, which I did. But now you kind of become dubious about their proof. That's my issue, if you accept their proof or not. Accordingly, it has different statements.
Okay, maybe I will show you prove this statement later, maybe.
No, I understand the statement. I don't understand the issue. If you accept Shun Yao, you don't need this if. From Shun Yao, it followed positive mass true for all manifolds. Right? Spin or no spin. And if you don't accept why before you refer to Shun Yao without mentioning that you refer to their theorem connected sum with the torus. Because from this theorem, if you know the connected manifold with the torus admits pneumatic positive Scalar curvature, then you have positive mass by this trick of Lockham long time ago, not this recent paper, but a fully accepted trick when you reduce to almost flat case. And if you have manifold flat at infinity, you just repeat periodically the pattern and you have torus connected sum with something. It's not exactly torus with connected sum with something, but it's manifold where Shun-Yao theorem, of course, applies. It has this, the technical lemma kind of applies to these manifolds. The key lemma, theorem 4.6, which I know, I refer to, yes, this is behavior of these singularities for any minimal surfaces anywhere. It's kind of local theorem. So this is my issue, my question about that. Okay.
Shall I go now?
Yeah, we can discuss this more at the discussion. After both lectures, there's a discussion,
okay.
So we should talk about this closely then.
Yeah.
Okay.
Now, my second result is that if polymath theorem is true for asymptotic hyperbolic manifold, then we can get these equalities. And then we get these ones. And then we can show that the polymath is true for all asymptotic flat manifold. In one word, that the validity of polymath theorems on asymptotic hyperbolic manifold would imply the validity of the polymath theorem for asymptotic hyperbolic manifold.
No, but this is the same issue. Modulation, yeah, it follows. Yeah. And this trick now due to this Galloway and company who reduce it by Lockham to asymptotically flat case. And asymptotically flat case follows from their lemma applied to some manifold with boundary. But see, their lemma is suffices. Their 4.6 theorem of Shun-Yao would apply that, if it is true. Very specific technical theorem about singularity. So I don't know about the intermediate statement, how they formulate it, but this lemma, it's what's called 4.6 theorem, it's imply everything. If it is true, I never checked the proof. I was not able to check it.
So to study the precise value of lambda plus of the Riemannian manifold is equivalent to explore the general polymath theory. This is my point. Okay. Now, Professor Gromov do have a conjecture on the explicit value on this quantity. That is, if this Riemannian manifold approach to standard sphere in certain sense, then the value approach to these ones. And under some extra condition that the positivity of the Gaussian curvature on the surface, we can verify this surface case. Now, here is the surface statement. Okay, all those things are on the topology sphere. So how about non-trivial topology manifold? Now, for instance, how about the non-negative scalar curvature field-in of the sigma with topology of like this? Now, we do have several results in this. Now, let sigma not be a convex hypersurface in Euclidean space, and its total mean curvature denoted by T naught, and omega G is an admissible field-in of product metric like this, so that the circle S1 component is homotopy and non-trivial in omega G. If so, we call it admissible field-ins. Then we can show that the total mean curvature of the boundary cannot be than this ones, 2 pi LT naught. And equality holds if and only if omega G is flat. Clearly, such this estimate is optimal. Now, this joint work with J.Chen, P.Liu, and Jingtian Zhu. And we will also have more specific values. If the gamma is flat torus, then we can get this. And also we have some more general results like this. And I think Jingtian will talk more later, so I will not go any further here. Now, here's a summary. So to study lambda plus of standard unit sphere is equivalent to study polymath theorem on symptotic flat manifolds. And to study this is equivalent to study polymath theorem on asymptotic ALF manifold. ALF means asymptotic local flat, and or ALG manifolds. So to study these ones, general lambda of general Riemannian manifold is equivalent to study general polymath theorem. I know nothing on this actually. Okay. So how about lambda plus ones? Here's lambda plus one means has positive scalar curvature field-ins. And by definition and with a simple perturbation argument, we can show that lambda plus one of Riemannian manifold cannot be the same lambda plus. And the following observation illustrates that we do have a strict inequality with certain non-degenerate condition. Now, here's a very simple observation. Let Sm be standard unit sphere, Xg be any non-negative scalar curvature field-in with positive mean curvature, and we assume Xg satisfies Sobolev inequality, which is called non-degenerate conditions. And we define the Brouwer mass like this. Then we can show that Brouwer mass actually has such a lower bounded. And if infimum of scalar curvature is positive, then we can show that Brouwer mass is positive. So we get strict inequalities. This is a very simple observation. Actually, now here's some remark. By counterexample of Minus conjecture due to Simobrando, Fernando Marcos, and Nevis, we have this point. Lambda plus one of the standard sphere is actually positive. That means we have many field-in of positive scalar curvature field-in of unit sphere. In particular, there are no rigid result in this. Now, recently, we can show by mu bubble argument that that hemispheres is only field-in of this two-dimensional standard sphere. With scalar curvature bigger than 6. This is n equal to 3. And H is non-negative, and we have these extra assumptions. Okay, now in the meantime, let me show you the relation between the lambda plus of standard sphere and polymath theorems. So now, before that, let me say a few words on polymath theorems. According to Gerald, the physical meaning of polymath theorem is that an isolated gravitating systems would have non-negative local mass density must have non-negative total mass measured gravitational at spatial infinity. As I mentioned before, that mass density can be interpreted as scalar curvature, and isolated system can be described by asymptotic flat manifold. Now, this is the definition for asymptotic flat manifold, and I think everybody knows this, so I will just skip it. And this is for a asymptotic flat manifold with certain decay conditions, we can define conserved quantity, which is called ADM mass or total mass. Now, let me just show you examples. Now, this is Schwarzschild manifold. Here's the underlying differential manifold is R3 delete a original point O. And this is a Schwarz metric, can be written as this way. This is Euclidean metric on R3, and this is conformal factors. And M is a positive constant. R is Euclidean distance to original point. So now this is two ends of symptotic flat manifold. And this ends corresponding to infinite point of R3, and that ends is corresponding to original point, okay? And M is total mass, ADM mass. Now we can formulate the positive mass theorems. Now let MG be a asymptotic flat manifold, and scalar curvature, if scalar curvature is non-negative, then ADM mass must be non-negative. And the equality holds if and only if MG is isometric Euclidean space. Now 5 years ago, Shen Yao proved that such kind of manifold admits no positive scalar curvature metric, and which implies the positive mass theorems. And this is also proved by Witten, if we assume that MG is M is spin. Now, to me, the philosophy behind the positive mass theorem is the following one. That is, the Minkowski space is trivial solution for Einstein equations, and it is solution with the least energy among all those with the negative energy densities. Okay, so much for positive mass theorems. Now, let me show you the following theorems. That is, if lambda plus of this unit sphere equal to this one, if and only if positive mass theorems is true on all asymptotic flat manifolds. In order to prove this theorem, we need the following lemma, which is called monotonicity lemmas. That is, let gamma t be a smooth path of non-negative scalar curvature on this sigma Riemannian manifold, and gamma t is assumed to be monotonicity increasing. That is, for any t2 bigger than t1, we always say gamma t2 is always bigger than t1. Then we can show that lambda plus of this Riemannian manifold cannot be bigger than that one. This is called monotonicity lemmas. Now let me show you the main idea of this. So pick up any non-negative scalar curvature fusion of these triples, which is denoted by omega m, omega g tilde, and then we use this to construct a non-negative scalar curvature fusion of these ones. Now here's the main ideas. Let G bar be like this, which is defined on the cylinder here outside is omega, and gamma t be defined like this ones, and then we try to modify this background metric G bar in this way. U is a function so that the scalar curvature of G is equal to 0, and the mean curvature of this boundary with respect to this G is equal to G naught, And this requirement actually is equivalent to the following evolution equation, or initial date with such kind of initial date. And this means scalar curvature equal to 0. And that means the mean curvature of this surface with respect to G is equal to H naught. And this is a very nice evolution equation. We can always solve it. Okay. Now, because gamma t is monotonicity increasing, and so is gamma t bar. And then that implies that the second fundamental forms of this gamma t bar of this slice, the second fundamental form of the slice with respect to this G bar is always positive because it is strictly monotonically increasing. And which implies that the mean curvature is positive, and this is a simple inequality. Okay, this is very simple calculations. And then we take derivative of total mean curvature of the each slice, and we get these ones. And each term is positive. So the derivative of total mean curvature of the slice and with respect to G bar is also positive. And that means total mean curvature, this is initial total mean curvature, cannot be than the T1 and gamma lambda ones. So this so that means the total mean curvature here cannot make sense here. Now we try to, the only things needed to do is to smoothify this metric, which can be always be done. And I should not go into details. Okay, so finally we get this one. This is monotonicity lemmas. Now let me show you that if quantum mass theorem is true on asymptotic flat manifold, would imply that these inequalities. First, we know that the unit bore is a trivial fusion of this, so we get these ones. And next, we can construct a quasi-spherical metric at the outside on Euclidean space outside unit bore, and we get these ones. And we can show that this quantity, which is generalized Bloch mass, is decreasing around this quasi-spherical metric and converging to AD mass of this metric G, and which is positive. So we get total mean curvature cannot make sense these ones, and combine those things and this thing together, we get this. That means quantum mass true would imply this equality is true. So next, we want to show you that if this one is true, then we will imply quantum mass true for asymptotic flat manifolds. Okay, we only need to do for asymptotic Schwarzschild case because of Xun-Yao's the density result. Now, this is a special asymptotic flat metric. We cannot. That means we only to check the quantum mass theorem in this for those metrics. Okay, now large sigma be a level set of the coordinate. Large sigma be coordinate sphere. We can define the quasi-local mass. We can define a generalized Bloch mass like this. And by definition, such kind of Bloch mass is always non-negative. So the key point is to show that the limit of those Bloch mass for coordinate sphere is equal to AD mass. And now R is just the Euclidean distance. So let me show you how to why this is true. Now first, we can calculate the mean curvature of coordinate sphere and get this ones. And then it's not hard to see that induced metric of the coordinate sphere is like this. So earlier, we can get area expansion like this. And then we get total mean curvature is equal to this ones. Okay. Now, next we want to calculate the lambda plus of total of the coordinate sphere. And we can get actually because the coordinate sphere is a level set of R, so we see this is truth. And beta is error terms. Because error term, we can estimate that the error term will go to 0 as R tends to infinity. And then by monotonicity lemma, we see that lambda plus of this equal to Z ones. And also we have this. We can estimate these ones. And then combine all those things together, we get that lambda plus of coordinate sphere is equal to this ones. So we get the limit of Bloch mass, it must be AD mass. And this is always non-negative, so M is non-negative, which is a positive, which is theorem of positive mass series. Okay, now, so last slides will show you summaries. So to study this lambda plus or unit sphere is equivalent to study positive mass theorem of asymptotic flat manifold. And to study such a lambda plus of such a manifold is equivalent to study the positive mass theorem on asymptotic of AOF or LG manifold. And to study this general value of this is to study general positive mass theorem. So there are very few results here. And also it is interesting to see what is this. I think I should stop here. Thank you for your patience.